Good afternoon, everyone, and welcome from your lunch break. Nemitari Ajienka, my second year, and I'm being supervised by Dr. Andrea Capilufi. And today I'm going to be talking about the strength of coupling as a predictor of their future co-change. And the main question of this research is it true that the strength of a coupling link between two software classes can predict their future co-change patterns? So I'm going to start by giving some background information and definitions. So I'll start with structural coupling between pairs of software classes. So according to Gearpol and Schweitzer, software system, object-oriented software systems are a network of classes which are dependent upon each other. And from classes, we can get instances of objects which depend on each other to make the software system function. A class can contain fields and methods, which basically describe actions each object can perform while the system is in function. And there's a direct dependency between two software classes if the dependent class cannot function without the independent class. So in the case of Java systems, the dependent class would not compile without the presence of the independent class, which it depends upon. So there's several types of structural dependencies. A class I could extend or implement another class J. A class I could call a method provided by another class, and a class could reference members of another class. So an example here, we have two Java classes, A and B. Create a link from A to B by creating an object of class B in A. And we instantiate that object, and it creates a link from A to B. And when we use B to call a method, we use the object in A, B, to call the method provided in B. We have a reference link from A to B. Depending on the structure of the system, we could have a network of classes which depend upon each other while the system is functioning. So we're trying to see if the number of links between two software classes could tell us how often they would need to be co-changed in the future. So in a real-life scenario, this could be in the car engine wiring diagram, using the number of cables maybe between the battery and some other part of the car system to tell how often we need to change both the battery and maybe the starter of the car together in future. So now we'll talk about co-change. Change dependencies are based on the change history of two software components. So in this case, we're looking at classes. And they're commonly treated as association rules. Change dependencies could reveal dependencies not captured by source code analysis. So most times we would not need to look at the source code to know how two components are dependent upon each other. Software change history is a set of commits submitted to a version control system by a developer. So when developers make changes to a set of components, they upload the changes they made to version control systems. And a revision or commit is a change in the history of a file or set of files. And like I said, a repository is a master copy of a software system where each changes are being submitted. And each software system has one repository. And the current ones being used are the CVS, Subversion, and GitHub. So the goal of this research is to look for ways by which we could reduce the coupling between pairs of components so as to make software maintenance as easy as possible for software maintenance. Because the more complicated a system is, the more coupled software classes are, the more harder it is to software maintenance to comprehend the software system. So up to now, the research on software change propagation has been looking at how a change in one class propagates to other classes in the system. Where we're taking a step back and looking at the starting points of where the change propagates. So we're looking at changes that occur between pairs of classes rather than the whole system. And this is to improve software quality and maintenance. And a more recent work in this area, a more related work, in this area, by Mondal and others, they found out that the higher connectivity between methods caused a higher code change of methods. So the more connections pairs of method had at the method level of granularity, the more times they were changed together. So this is like our motivation diagram. We're trying to see if the number of links between two classes could tell us how often they will be changed together over time. So for example, looking at the classes A and C, they've been changed twice during the change history of the software project, and they have the highest number of links between them in the system. So the main goal is to answer the research question if it is true that the strength of the coupling link between pairs of classes can tell us how often they'll need to be co-changed in the future. So to answer the research question, we extracted the structural coupling between pairs of classes at every point in time. At every snapshot of the software project, we extracted the coupling metrics between pairs of classes, which include the number of links between them and the number of methods involved in the calls between both classes. And also for the change dependencies, we extracted a list of classes that were changed at each point in the system to know how often pairs of classes were being co-changed. So we studied 10 software systems, and we looked at the distinct number of pairs of coupled classes, number of pairs of co-changed classes, and the intersection between them, just to study the interplay between both types of dependencies. And in most cases, in all cases, the number of coupled classes were less than the number of co-changed pairs of classes. So for example, in one of the software projects we studied, we had 108 pairs of coupled classes at the source code level and 9,635 co-changed classes. So 9,635 classes that were co-changed but not coupled, and 108 pairs of classes that were coupled but not co-changed. And in between them, we had only 727 pairs of classes that were both co-changed and coupled. So to answer our research question, we used the Wilcoxon ranked sum test to test two null hypotheses. One is that we tested for equality of the software metrics between pairs of classes that were in each co-change cluster. So we introduced co-change clusters, including pairs of classes that never co-changed, the pairs that were co-changed once, and pairs that were co-changed in a relatively small number of revisions, and pairs that were co-changed frequently. So we tried to see if the software metrics, coupling metrics between pairs of classes in each cluster were different. So we could use those metrics to predict the co-change pattern in future. So interestingly, our results revealed a difference in the metrics between pairs of classes in various clusters. For example, in this case, the coupling matrix between pairs of classes that were never co-changed was 100% different from those that were co-changed in a few times. And also in the directional test, we checked if the metrics from one cluster were greater than those in another cluster. And in a few cases, this was the case. And in other cases, the metrics in one cluster were less than those in another cluster. So for example, the pairs of classes that were co-changed frequently, the metrics between pairs of classes that were never changed was higher than those that were changed frequently. So to summarize our contributions, we saw that coupled pairs of classes are always smaller than pairs of classes that are co-changed. This means that inferring structural coupling from co-change will produce a lot of false negatives. And also using the coupling information between classes can also infer their future co-change pattern. We also saw that pairs of classes do not follow an 80-20 distribution, whereby 80% of the problem is caused by a few number of items. We also saw the correlation between coupling strength and the co-change clusters, as the metrics in the different clusters followed different distributions. So for future work, we would like to generalize our results, as we only studied 10 software projects. We have a list of 222 projects which will push our study further. And we also plan to build and evaluate prediction models to predict co-change patterns of pairs of classes, of newly added pairs of classes to software systems. So we'll train on the previous set of data and try to predict for the new classes from second revision upwards their co-change pattern. I would also like to explore the interplay between conceptual coupling and logical coupling. For the conceptual coupling, we're building a tool to use vector space modeling to extract semantic coupling information between pairs of classes from their corpus. So the take-home message from the study is it's possible to predict the co-change pattern of pairs of classes in Java software systems. Thank you.